We spent all of chapter 2 looking at quadratics. That's where the equation generally would start out with x to the second power. Moving into topic 3, we're going to look at polynomials, and those have powers with even bigger numbers than 2. So for section 3.1, we're looking at how the key features, which we talked about in topic 2, are helping us sketch the graph. So we're going to be working with polynomials and how giving key features to help us sketch the graph. With the explore and reason for 3.1, they're just going to have you try by exploring, graph a few of them, like x to the first, or x to the second, or x to the third. For part A, it wants us to graph all the odd powers. So here you'll see x to the first, x to the third, x to the fifth. If we look here at all the odd powers, I've graphed x to the first in red, x to the third in blue, and x to the fifth in green. And we can kind of notice a few similarities, but they just want you kind of to explore what might be the same and what might be different. Now, one thing I've noted down here, they're going to ask you about quadrants. It might say, which quadrants do they pass through? If you recall, or if you've ever learned them, quadrant 1 is in the top right, quadrant 2 is in the top left, quadrant 3 is in the bottom left, and quadrant 4 is in the bottom right. We could say that all of these graphs are located in the first quadrant and the third quadrant. That's when the power was odd. Now, if we look at when the power is even, and I would look at the red one, which would be x to the 2, and the orange one or yellow one would be x to the 4th, and the green one would be x to the 6th. That's for part B. All of these have an even power, x to an even power. We note that they're all in quadrant 1 and quadrant 2. So those are some similarities. These ones generally look a lot like each other. And one thing we might be able to conclude here at the bottom is that if the power is even, the graph ends in the first and second quadrant. If the power is odd, the graph ends, if you will. Both ends are in the first and the third quadrant. We'll be talking about end behavior quite a bit. A lot of this section is vocabulary. So we have some key terms here. We look at this function negative 4x plus 9 plus 2x to the third. Maybe it bothers you a little bit. Normally we write these in a little bit different order. Let's see if it makes sense to you. So they would say, let's rewrite it in standard form. So I'm kind of going to jump around here. A standard form would mean all the like terms are combined and the terms are ordered by degree in descending order. So in this case, I see that this has a degree of 1, negative 4x. We don't see the 1, but there'd be a 1. So it's not in a descending order. It doesn't go from the biggest to the smallest from left to right. So here we might write our equation in standard form, 2x to the third minus 4x plus 9. We might ask, what is the degree of that? Well, the degree is actually the greatest degree or power. That's what we call the degree of a polynomial. So this degree is going to be 3 because the highest power we see, and now it's up front when we wrote it in standard form, is 3. Then how many terms are there? There's 3. The negative 4x is a term, the 9 is a term, and the 2x to the third is a term. One other thing, the leading coefficient, that is a constant that's with the term in the highest degree. So since I've wrote this equation or polynomial in descending power order, the one that's first is our leading coefficient. So if I highlight here, that would be this 2. It's the number or the coefficient next to the term with the highest degree. They ask why it's important to identify the degree or the type and the number of terms. That's because then we can be on the same page when we're referring to it. One thing we could note is that anything that has 3 terms would be called a trinomial. One was pretty easy. You could do the try it on your own and check the answer key on Canvas. I think you'll find it pretty simple once you remember what each vocab word means, and don't forget to write them in standard order. That means you want the highest power to be written first and then descend from there. Now for example 2, we're going to look at an odd degree polynomial. So what that means is, remember, when our power is odd, so 1, 3, 5, When we look at an odd degree, we have some notes here, and you'll find these notes on your answer key on Canvas for our packet. But we could see that when we did the 1 or the 3 or the 5, all of these odd degree polynomials generally tend to end up in the first quadrant and finish down in the bottom left quadrant here, or at least their ends are both in those quadrants. We also see in this odd degree one over on the right here that it goes to the left top second quadrant and to the right bottom fourth quadrant. So they're kind of kitty cornered of each other, if you will. That is always the case. One thing we need to note is end behavior up here in our vocabulary is as x approaches infinity, y will approach as either a positive or a negative infinity. And you'll find this to happen a lot on your homework that you're going to do. So we're going to use this notation down here. When we look at these three graphs, odd degree with a positive coefficient, so 0.5 or 2, we would say as x goes to infinity, so as x gets really, really big numbers out here, our y values go up, 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 up to the positive infinity area. They're going to go up forever. We see this little end behavior too. They're kind of split. It goes up to the right and down to the left. Whereas when we had an odd degree with a negative 0.5 or a negative 2, they went the opposite direction. Okay, but we also want to note this, this notation here. X goes to infinity as x goes to infinity, rather, y is going to negative infinity. So as I start at 0 here, when x goes out farther and I scan across this x-axis to the infinity area, the y values of these graphs are going down to negative infinity. And that will always be the case with an odd degree and a negative leading coefficient. Notice our end behaviors are split in opposite directions again, but this time going down towards the right. Now we have a slide with even degree. End behavior again, as x goes to infinity, y is going to either go to positive or negative infinity. And so when we look at these even degrees here, we have a 2, a 4, a 6 power. All of those both end in the upwards direction. So one thing we're going to look at with this notation over here is as x goes to infinity, y is also going to infinity. It's both finishing up to the right there. Whereas here, when x goes to infinity, when we have a negative coefficient, the y value goes down to negative infinity. So we want to look at this notation again. You'll notice that in both of these boxes up top here, I like to remember when it has an even degree, whether it's a positive or negative, they're both going to go in the same directions. So either both up for even and a positive coefficient, or both down for even degree and negative coefficient. So you'll start to catch on to those patterns. That's really all we're looking for. I'm just going to touch base here on the try it, for example, too. Down here by the habits of mind, if your leading coefficient is positive, okay, and notice we're only looking at an even function here. When we talk about the even function, if you have an even degree for the highest power, they'll either both end up, the end behaviors will both go up if it's a positive coefficient, or they'll both go down if it's a negative coefficient. So here I'm going to look, this part A is in descending power order. I look at the beginning and I notice there is an even degree and a positive coefficient. So I would say as x is going to infinity, then my y value, because I know it's an even power, they're going to match each other. They're both going to go up or they're both going to go down. And the number out front is positive, so they're both going to go up. So since that's up to infinity, the y value will go to infinity. Whereas here, I have an odd degree. Now remember, an odd degree isn't like this even one down here. Odd's going to go in the opposite. I think O is for odd and O is for opposite. So we have an odd degree and a negative leading coefficient. So as x goes to infinity here, we're going to have our y value go to negative infinity, because if we look back at our notes here, when you have an odd degree with a negative leading coefficient, it will always go down to the right. Picture this little arrow right there.